Hey guys, in this video I'm going to go over some of the most difficult questions from the Unit 5 mid-unit test, and then at the end of the video, after you watch the whole thing and answer the questions, you'll be given the password to the Unit 5 mid-unit test, and you can use that to retake the test. So remember, pay special attention to the video here. These are statistically, these were the hardest questions on the mid-unit test, and so hopefully this will help you get a better score on your retake. Number one here, or the first question I have listed at least, in the diagram, which of the following represents the energy of the products? And then you had four answer choices, and lo and behold, they were A, B, C, and D, and you're deciding which one represents the energy of the products is the key word here. And hopefully we've seen enough of these graphs now that this is starting to look familiar, right? And we know this is the reaction progress, and then we have energy on the y-axis, and so the start is right here, and then finish would be over here, and then low energy down at the bottom, and it increases in energy the higher up you go on the y-axis. And so we can look at each of these, and we're saying which one represents the products. And hopefully, like I said, you know by now, and actually if you look at the graph below it, you can see where the products are, is that we start with the reactants at C, so this is the reactants. A, hopefully we know this increase here is the activation energy. I'm just going to put active energy. B is the change in energy between the reactants, and then D is the products. So B is kind of the change in energy between the reactants right here and the products right here, these two blue lines. So that's the difference in energy, or the change in energy between the reactants and the products. And it's asking us which represents the energy of the products, and so clearly B right here is, and we can follow the blue line over, that would be how much energy the products have, and so D represents the energy of the products. If it had asked you which one represents the energy of the reactants, then you could put C. If it asked you which one represents the activation energy, then you would put A. Alright, next one. In an exothermic reaction, which of the following conditions will be true? And this was a tricky one, and you have to think about this one closely because the answer choices were asking you, it was activation energy minus something, and then it was said greater or less than activation energy minus something else. Okay, and I went ahead and I grabbed the answers here because oh no. There we go. Sorry about that, guys. I accidentally deleted the answer choices, I guess. So I did go ahead and grab the answer choices for this one because I think it'll be easy to talk about if we can actually see what the what options you had to answer. So we're looking at an exothermic reaction. If it's an exothermic, if it's asking you about an exo or endothermic reaction, guys, it might either be good to draw out the exothermic graph, or have a diagram. I would memorize this diagram and then draw it out when you're asked these questions, and so that way it's a lot easier to think about than just trying to think about the whole thing in your head. If I were taking a test, I would have to draw this out to make sure I was getting the right answer. And so then it's asking you, and you can already see the correct answer here because it's bolded. I would have to retype them all to make it not bolded, but that's okay. So if you look at the choices, we have activation energy will be less than the energy of the reactants. So here's our activation energy, right, in between these two dashed lines. And it's saying will be less than the energy of the reactants, and that's not necessarily true, right? This activation energy, it could be really big, right? And maybe the reactants line is moved down here, and so it's really small. So that's not necessarily true. Activation energy minus energy of the products will be greater than the activation energy minus energy of reactants. Okay, so this is a mouthful. Let's take it step by step. Activation energy minus energy of the products. So here's our activation energy in between these two dotted lines, minus energy of the products. And remember, it helps sometimes to give these actual numbers when you're doing this. And so let's say that our products here, let's just say it's 50 joules. Let's say our activation energy here, let's say this is 25 joules. And let's say our reactants, let's say this is 100 joules. So activation energy minus the energy of the products. Okay, so it would be 50 minus 25 equals, okay, so that would be 25 joules, will be greater than the activation energy minus energy of the reactants. Okay, so energy of reactants is 100 minus activation energy is 25. That's 75. And so this is not true, right? Because this is saying activation energy minus energy of the products will be greater, and it was 25, than the activation energy minus energy of reactants, which was 75, and that's not true. 25 is less than 75. So let's look at the next one here. This one says activation energy minus energy of the products will be less than activation energy minus energy of the reactants. So it's saying the same thing as this one right here, but it's just saying less than. So that is true because activation energy minus products is 25, activation energy minus reactants is 75, and so yep, the products is less than that of the energy, activation energy minus the reactants. And then we can check here on the last one, activation energy will be less than the energy of the products. And once again, that's not necessarily true because we could have a really big activation energy and a really small energy for the products. So the bolded answer right there, that would be choice C, is the correct answer. Like I said, drawing out that graph, I think, and then maybe putting in example numbers like I did will really help with those. Alright, so the drawing shows a chemical reaction between hydroxide and bromomethane to produce methanol and bromide ion. The middle drawing is the activated complex. The reaction is exothermic. Which species has an energy level that is between the energies of the other two? This question is difficult, I think, because of the way it's worded and the fact that it's using, you guys might not know what hydroxide, bromomethane, methanol, and a bromide ion are necessarily, but you don't need to know what those are. You need to know that the middle drawing is the activated complex. Remember, that's also called the transition state, though it's the same, just different terms for the same thing. Transition state. And so we know we're starting with this, with A, so this is the reactants. And then we're finishing over here, so these are the products. So now, hopefully this is making more sense, and you're thinking about this like a normal chemical reaction, right? We have reactants, start with reactants, goes to a transition state, and then we have products. It's telling us the reaction is exothermic, so I would draw out your exothermic graph if you're doing this on a test, and we have one right there we can look at. And then it's saying which species has an energy level that is between the other two. Okay, so then we just have to use our graph and look. So here's our reactants. Our activated complex would be on top here. I can write it activated complex, aka transition state. Remember, activated complex and transition state mean the same thing. And then our products, of course, are down here. So I can look, and it's asking me which species has an energy level in between the energies of the other two, so which one's in the middle out of those three as far as energy goes. And I can see here my activated complex has an energy right here, reactants energy right here, products, energy over here, and so clearly then my reactants are the one in the middle, right? Activated complex has the highest energy, products have the lowest energy, and reactants have in the middle. So the answer would be reactants, or A. How are we doing with time? Okay, we have enough time here. On to the next. In an exothermic reaction, which of the following conditions will be true? So again, it's asking about an exothermic reaction. I would draw the exothermic graph, and so here's our exothermic graph again. And then we have the following choices here. Activation energy will be less than the energy of the reactants. Oh, we did this one already. I apologize, I put that on there twice. That's the same question that we just did. So which of the following will increase the number of collisions and energy of reactant molecules? And again, I went ahead and grabbed the answers because I think it'll be easier to talk about like this. So which of the following will increase the number of collisions and, this is the key word in this question, and energy of the reactant molecules? And so now here's our choices. Let's think about them individually. A here, increasing the concentration of reactants. So if we increase the concentration of reactants, yes, that will increase the number of collisions, but it will not increase the energy. And you can think of that, right? If you have a classroom with 10 students in it and they're walking around at a normal speed, and then you increased it to 50 students in the classroom, there would definitely be more collisions, but they're still just walking at the same speed, and so each individual molecule does not have any more energy, right? We didn't change the energy of each molecule, we just added more of them, and so there's more collisions. So not A. B, adding a catalyst, and here you just need to remember what a catalyst actually does, and remember a catalyst lowers the activation energy of a reaction. So it increases the speed of a reaction by lowering the activation energy. It does not affect the number of collisions or the energy of the reactant molecules, so it's not B. C, increasing the pressure of the reactant mixture. Sorry, you can't see that last word very well. It's mixture. And so remember, if you increase the pressure of the reactant mixture, it's the same. If it's a gas, it's similar to increasing the concentration. And you can think of that if we have the balloon, right? And then we increase the pressure outside the balloon. We're thinking increasing the pressure outside the balloon, pushing in on it, and so the balloon gets smaller. And if we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? We still have 10 molecules. They're just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're just a lot closer together in a smaller volume. And so we have increased the concentration and we've increased the number of collisions. However, again, we didn't change the energy at all. We just put the same 10 molecules in a smaller space. And you can think of that, maybe there's 10 students in a big gymnasium, so they're not going to run into each other very much. And then we put those 10 students in a small classroom. They're still walking around at the same speed. They're just in a smaller area, and so they run into each other more. So it's not C. D, increase the temperature of the reactant mixture, and that will increase both collisions and energy, because you can think of that as like 10 students in a classroom and they start off walking around really slowly. And then if we increase the temperature, remember, we increase the speed. And so molecules that are traveling faster have more energy. It's like students running around the classroom now. And so they'll run into each other more often, right? There'll be more collisions. And they'll run into each other with a lot more energy because they're traveling faster. You can imagine yourself walking into someone versus running into someone, and you have a lot more energy when you make a collision when you're running. So the answer is D, temperature increases collisions and energy. Last one, which of the following conditions increases the frequency of collisions without changing energy or concentration? So this is a similar question to the one we just did. And we said here A, increasing temperature, that does increase the energy. So it can't be that, because remember we went without changing the energy. B, adding more reactant molecules. Nope, can't be that. That would be changing the concentration, right? If we had, that would be like a classroom with 10 people, and then we added 50, and then we added 40 students, and we had 50 total, right? We'd have a higher concentration. D, increasing the pressure. Again, increasing the pressure is the same thing as changing the concentration if it's a gas. And so it has to be increasing the surface area. Yeah, we don't change the energy, we don't change the concentration, there's just more area for reactions to occur. Alright, that's all we have time for, just a couple seconds left. Make sure you write down the password at the end, and good luck.